Our last major topic, and then a couple of little review slides, empirical formulas. So I believe this came out of chapter 8. Empirical formulas are our fully reduced whole number ratio of elements within an individual compound. So let's take a look at some potential examples. If we were to look at a compound of sodium chloride, pictorially, it might look something along these lines. I think I've inverted the colors from our past examples, but that's okay. We've got, say, sodium chloride in this example. In this case, there were 5 green balls, and we'll be more generic. So 5 green balls, and then 4, which is going to become problematic. So we'll add a 5th purple ball. And so we could reference what we're seeing there as green 5, purple 5. Because the symbols could be confusing, we could switch it up to sodium 5 and Cl5. The problem with that kind of notation is that what happens if I add, say, another sodium and another chloride? Well, now it becomes more complicated and we get more and more pieces stacking into this. So what we decided is that what we're going to do is take for our ionic compounds and always represent that smallest whole number ratio. And if we're going to keep this color coded, we'd go with NaCl. And so what we've got there is now a formula for the ionic compound sodium chloride, and we just assume that whatever we're looking at scales upwards from there, maintaining that ratio, which is great for ionic compounds because we're now always that reduced ratio. And what you might have noticed is that when we talk about ionic compounds, at least in the textbook, they don't reference it as a molecule, they reference it as a formula unit because it's the smallest reduced unit. So when we look at our ionic compounds, we'll always see them kind of following this pattern. So magnesium chloride, we would get MgCl2. And so why are we specifying it just as those 1 and the 2? Well, for every magnesium, we need 2 chlorines. Okay, so our ionic compounds have a relatively straightforward system. But what happens when we move to a molecular compound, say like benzene? Well, if we're going to spend the time to draw out benzene, don't stress that you don't know how to draw benzene, because it's not a big deal. But if we go through and draw this out, and you can clearly tell that it's a problem for me even, because we don't have a lot of space on this slide, and we've got our Lewis structure for benzene, which comes in as C6H6. If we follow the same patterns that we just used for ionic compounds, our formula becomes C1H1. But if we look at a molecule of benzene, it is not a repeating unit of multiple carbons with hydrogens alternating all the way out. It follows this is in that red box is the structure of benzene. And so when I have more molecules of benzene, I have more of that piece repeating elsewhere. Not C1H1, but C6H6. So a molecular compound has a different formula format, and we can't do reduced ratios per se with our molecular compounds. Why the per se? Well, it depends. The actual compound is going to be C6H6, but if I go through to study the atoms that are in it, I don't know what that exact ratio is, and what I may end up discovering is what is known as the empirical formula. So the empirical formula is that reduced ratio. This is roughly equivalent to our ionic formats. The C6H6 is our molecular format. The molecular format is unique to our covalent compounds. So we need to have some kind of understanding on how we can manipulate between these things and kind of understand what's going on with it. So when we're talking about our empirical formulas, it's referencing the subscripts that we associate with those. Okay, well, before we start pushing into anything to do with the calculations that are involved in some of this, what do those numbers mean? Okay, so if we take a look at magnesium chloride, there is an implied 1 next to the magnesium. What that means is that when I build what's in that black box, I need 1 green ball, and I need 2 purple balls. This is now the compound magnesium chloride. Okay, So it's the number of those things that moved in. So that could be atoms, that could be molecules. But as we talked about in chapter 8, we don't look at atoms and molecules anymore because we can't measure those. We can't observe those easily. So what we need to scale up to is not atoms and molecules, but those numbers are now going to refer to the moles. Okay? And by now, they've been referring to moles. But what we're now going to use is recognize that that's what that unit means, so that when we're given information about a compound, we can now convert those numbers into a empirical or molecular format. Okay, this process is one that is used frequently in the past and is probably becoming a little bit less prevalent now that we have more advanced techniques. But it does allow us to really drill down into what is the meaning of our individual formulas. And for that reason, it is something that we still discuss and talk about in class. Okay, but to me, really, we can do that in other ways, which means what I'm really pushing is kind of a formula interpretation of these things. So to go through and solve an empirical formula, these are the steps you need to move through. So people have been asking for steps. Here they are. These are the steps you would need to move. As soon as we hit molecular, those are the steps that we would need to move through. Okay? I will point out, and I'll point out again when we do it, that this number 2 is in reference to that step number 2. Okay? So let's go through and look at a couple examples. So, in this case, if we have an unknown compound of radium oxide found to contain 0.726 moles of radium and 12.3 grams of oxygen, what is the empirical formula? Okay, and that's an of. So right out of the gate, we actually have a problem with this question. And so we'll look at another example here in a second that fixes this issue. We're looking at the compound of radium oxide. And this is immediately an issue because radium is a metal and oxygen is a nonmetal, which means we are now attempting to solve for the empirical formula for an ionic compound, which is silly. Let's go with silly. Okay, and that's because we could figure that out based off of the charges on those individual species. Okay, so let's not stress on the nuances of that and just kind of plug and chug our way through. So what we're being asked for is what are the X and the Y being associated for each of the radium, or for the radium and for the oxygen. And for those of you trying to do charges, don't. Okay, remember, focus on the intent behind this. The intent is recognizing moles. So we could go through by looking through the rest of our questions, or the rest of the given information, and we could find that there are 0.726 moles of radium. Okay, well, in our formula, that X and Y we said were moles. So right away we could say, well, X then must be 0.726, and I should be writing that as a subscript. Okay, that should send up alarm bells because the only numbers that go in as subscripts are whole numbers. So 0.726 isn't going to work for us. Okay, we're going to have to get that into a whole number ratio, which is the key point of an empirical formula. But to get the ratio, I need the moles of radium, yes, and I need the moles of oxygen. No, I have grams. So the very first thing that I'm going to go through and do is organize some of this. I have 0.726 moles of radium. I need the moles of oxygen. How do I get moles of oxygen? Well, what given information do I have? I know I have grams of oxygen, 12.3 grams of oxygen. I need the grams of oxygen to become moles of oxygen. That is found by looking at our periodic table. 16 grams of oxygen is 1 mole of oxygen. Why can I get away with just 16 and not 32? This very specifically says atoms, which clarifies that for us. So I can now go through and enter that into the calculator to get a number of moles of oxygen in this individual compound. And now I'm talking kind of through something else while I run the calculation. And we get a whopping 0.76875 moles of oxygen. And yes, that's a lot of sig figs, but that's kind of addressing the next point. we want a ratio between these, a reduced ratio. To figure out the reduced ratio, divide them both by the smallest number. Well, 0.726 is our smallest number, which means the reduced ratio for our radium will be 1 radium. And our reduced ratio for our oxygen, 0.0726, will be 1.0589 oxygens. Okay, well, that's not a perfect ratio, but that comes darn close to 1, meaning our whopping answer becomes 1 radium, 1 oxygen. Okay, do we need the ones? Nope. And our formula, or our empirical formula for this, would be RaO. Okay, so what we're just trying to do is to get those into mole units and build a ratio. That's it. Okay, so what we've got here is a slightly more complex question. This one's a little bit better because it's carbon and hydrogen, so we are looking at nonmetals. So we have an unknown sample, 24 grams of carbon and 2 grams of hydrogen. Again, if we summarize what we're trying to do, we have carbon and hydrogen. I want to know the ratio of X to Y. What are those values? Now, you can't cheat with looking at your charges because it's not going to work out. So what we're going to have to go through and do is figure those out by coming up with our calculations. X needs to be moles of carbon. How do I get moles of carbon? Well, what do I know about the carbon? I know I have 24.0 grams of carbon. I need the grams to become moles, so grams of carbon in the denominator, moles of carbon in the numerator. Okay, look at the periodic table, 12 grams, 24 divided by 12 gets us a whopping 2 moles of carbon. If we move through now to our hydrogen, so let's go ahead and switch up that color. So our hydrogen, we want to know how many moles of hydrogen we have. We started with 2.0 grams of hydrogen. How do we convert grams of hydrogen to moles of hydrogen? Again, periodic table, 1 gram of hydrogen is 1 mole of hydrogen, and I get an answer of 2 moles of hydrogen, which means we could go through and say our formula was C2H2. But remember, it's supposed to be the reduced ratio. So to do that reduced ratio, which number is smaller? 2 or 2. Thankfully, they're both the same. And that reduced ratio comes out to be C1H1. Ta-da! We followed all of the steps, and we now have that empirical formula. Okay? That's the point of empirical formulas, just getting down to what that ratio is. And the whole point of this is acknowledging that those numbers mean moles. So regardless of the information given to you, convert it into moles, and then you're good to run. Okay? That's the point of it. What do we do when we move to a molecular formula? Well, the molecular formula and the empirical formula are related to each other. Okay? The empirical formula is the reduced ratio. The molecular formula is the actual ratio, which means they are related to each other through a single whole number ratio. So if we again look at our question here, we know that our empirical formula, because we just ran this calculation, comes out to be C1H1. The molecular formula we are trying to determine in this case, because that question asked the same thing, so I forgot to advance it, so there we go. If we use that exact same sample, we found that our empirical formula was C1H1. Our molecular formula is what we're now being asked to solve for. CXHX. And now I can use the same symbol because, according to the empirical formula, it's the same number. So that means if I can determine X for carbon, I now know the number of X for hydrogen. How do I figure this out? Well, it's going to come back to the mass for each of these individual species. The mass for the molecule has to be given to me in the question. In this case, it's given as 78 grams per mole of CXHX. in both cases. So one method for this, okay, a bit of a brute force, but we know the mass of carbon to be 12 and we know the mass of hydrogen to be 1. So could it possibly be just C1H1? Well, then our mass would be 13. That does not equal 78, so no, can't be 1. So then what could I do? Well, I could try and say X equals 2. That would mean 2 carbons, which would mean 24 plus 2, which equals 26. That does not equal 78, so X can't be 2. Okay, so we could continue to go through and do this until we figured it out. Okay, what we're effectively doing is just guessing and checking. There is a faster way. That faster way is to realize that it must be a multiple of the empirical mass. Okay, these two are related to each other through a whole number, which then means the masses must be related to each other through that exact same whole number. So what is the mass for the empirical formula? Well, 1 carbon weighs 12, 1 hydrogen weighs 1. The empirical mass is 32. What's the whole number difference between them? We'll take 78, divide it by 13, and what do you end up with? You end up with the whole number of 6. So the whole number mass relationship is 6, which means the whole number molecular relationship will also be 6, which means my formula is C. 6 and X sound too similar. 6, H, 6, and there's my molecular formula. Okay? For those of you being like, I just want to try the brute force way, well, as you continue through all that process where all that work didn't work, we could erase all of that and we could go through and verify this. C6, so 12, because there's a mass of 12, times 6 is, I think I did that math wrong. 6 times 12 is not 70, it would be 72, okay? Plus 6 times the mass of hydrogen. Let's follow the same pattern. Hydrogen weighs 1 times 6, which would be 6. 72 plus 6 is 78. There's our molar mass. So everything adds out correctly. Okay? So again, these are the steps that you would go through to solve both the empirical and molecular formats. Okay? What we went through and walked through here was just 1A, grams to moles, to get us our mass. Okay? But you could be given the statement where it's percent composition. So it is 12% carbon and 82% hydrogen. I can't do math, clearly. Was it 88% hydrogen? If we had that system, what we could go through and do is say, well, let's just say we have a 100-gram sample. That 12% of 100 grams would be, well, 12 grams. I now have a mass amount that I can go through and use according to the rules of A. Okay, so that's the intent behind that. With a percent composition, just make it a 100-gram sample and then your calculations will run smoothly. You don't have to think about any kind of weird conversions. It converts quickly and efficiently. Okay, so that's the recommendation. You can use any mass amount you want. It's just that a 100-gram sample is easiest. Okay, and that's our empirical and molecular formulas. Okay, after that, we've got our review. Okay, so as far as I'm concerned, this is the new content moving into Unit 3. So dimensional analysis isn't really new, okay, but we're using that process again and again and again. The new things, we get a mole of objects is 6.022 times 10 to the 23rd objects. Okay, not measurements, objects. Why is that useful? That allows us to say that the periodic table is giving us a number of grams per mole for whatever atom. Balanced equations give us substance conversions. Note in that equality, what's happening? We're switching A to B. The measurement of moles stays the same. Okay, molarity gives us a number of moles per liter of solution, which is fantastic. When we move to gases, okay, we get that super irritating conversion of 1 mole of a gas equals 22.4 liters. Do not confuse these things. Okay, they are very, very, very different situations. Okay, it is easy to get those confused, but be careful with it. Solution versus gases. Okay, so watch out for that difference. The other thing that came out of our gas section was our PV equals nRT. After that, we're now looking at our applications of everything above. We've got our limiting reactants and or reagents, depending on how you want to reference it. You've got percent yields, empirical formulas, and molecular formulas. So all of these things are now showing up in this next unit, okay, or this next exam. And that makes this exam challenging. Virtually every single one of these involves a calculation. You're going to need a calculator handy. You're going to need some work or paper handy when you go through to solve these things, because you need to ensure that you're putting those pieces together correctly. Okay? If we push through to more review slides, these are slides that I had up on past things. Not sure how much I really like them, but this does show you where a lot of those conversion factors can be found. So if you're struggling through some of the homework, you can go through and look at this to help you find that information. More on conversion factors at the bottom helps to kind of show some of those interconversions that you can do. The reason why I like this particular slide is this big thing way up at the top here. Okay, measurement and substance. Every unit has a quote-unquote measurement unit and a substance unit. When we're doing our conversions in this particular section of the semester, you need to make sure that every time you write a unit, you are including a measurement and a substance. The instant you leave one of those off, your calculations will usually crumble. Okay? Follow your dimensional analysis process. I have every faith that you guys can put this together and crunch it out. Spend some time practicing it. Send me questions when you've got questions. Take pictures of your work. Put pictures of your work up in front of cameras so that friends can see it. Okay? Put pictures into the Google Docs that I'm sharing with you guys so that you have the ability to kind of feed off each other and help everybody advance through this class. Okay? So with that, that is the last lecture for Unit 3. Woohoo! No more videos for this unit.